All right, so it's my pleasure to introduce Peter Kraus, who's a researcher in Amsterdam, and he's really specialized in the development of new techniques for actually probing what goes on during semiconductor manufacture, and in particular in nanolithography and EUV sciences. And so, Peter, we look forward to hearing what you have to say.
Thank you. That is working. Yes. Just test that quickly. Yes, thanks a lot. Thanks for the kind introduction. Indeed, my name is Peter. I'm an associate professor at the Free University Amsterdam, and I'm mainly placed at the Advanced Research Center for Nanolithography, and I'll spend a minute to explain what that actually is. So much of the talk today will actually be about optical characterization techniques for semiconductor nanostructures, not so much the material science part. So understand that's the background of many here. So if you have any questions at any time, please just ask. We'll try to make it fun and interactive as much as possible. So what is that place where I work? ASCNL is a research institute. That's a building, that's a group of people that works there. It's about 100 people. What is special about us is we are connected with the universities. I'm formally employed at the Free University. Others are at the University of Amsterdam. These are the two main universities in the city. But really, the special part is that we're very strongly linked to an industry partner, and that is ASML. So many of you know the Netherlands mainly for the tulips or the wooden shoes and maybe other combustible items. But actually, I was waiting for that, good. But there's a very significant company that's actually responsible for about 70% of the world market share in nanolithography, and that is ASML. It's by now the third largest company in Europe by market capitalization. So yeah, the special part is that we have a lot of projects with them and work very closely together. Oh, here we go. And the mission is ASCNL focuses on the fundamental physics and chemistry in the context of technologies for nanolithography, primarily for the semiconductor industry. I think I will probably click by hand. Somehow that's... Yes. So my specialty is high harmonic generation. And you can see there what high harmonic generation is. It's basically a very strongly light-matter interaction where you shoot a very intense laser beam onto a gas expansion. And through a highly nonlinear light-matter interaction, these infrared photons are converted all the way into the soft X-ray range. That is an extremely useful tool for many different things, including applications in semiconductor metrology. That's what I'm, to some extent, going to talk about today. And as we have already heard a few times, of course, PIs usually don't do much in the lab anymore. So it's actually all these people. That's my research group in Amsterdam that do all the work. Okay, briefly, what is the sort of vision and mission of the group? In general, we work on, as I said, high harmonic generation, both from gases and from solids. That's a more recent advancement that has become quite popular. And the materials we look at are, on the one hand, semiconductor nanostructures, which is mainly what I'm going to talk about today. But more on the fundamental side, we're also interested in condensed matter physics problems, particularly looking at strongly correlated materials and resolve their intrinsic dynamics, both with high temporal and spatial resolution, meaning nanometers and femto to sub-femtoseconds. So our overall mission is to push high harmonic generations for metrology applications, broadly speaking, for all these classes of materials. And the vision, sort of what I want to have achieved in 10 years, is that we can have a sub-femtosecond and nanometer resolution, both of a current flow in an integrated circuit and also of the intrinsic material dynamics in a strongly correlated material. I'm going to talk to you a bit how we get there today. Now, in the spirit that this is a summer school, I thought I should really also go a bit to the basics. So I want to give a general introduction to nanolithography and wafer metrology. Then I want to spend some time on what I believe, are the most important metrology techniques that are currently used in industry. Already heard yesterday there are about 1,000 steps, so probably 100 of them are metrology, or 50. So I picked out 4 now. So this is a bit of a biased view that I'm giving here, but I think these are the very, very important metrology techniques. So this is about half of the talk that I want to spend on that. So if I'm going total, there's a clock, so never mind. I was about to say you can give me a sign, but I can watch it myself. And then I will go a bit more into more developments in research and what we are actually doing. All right. You're probably familiar with that, but just to make sure we're on the same page, how do we actually make a computer chip? Typically start somewhere here. You take a wafer and you apply a photosensitive material, which is what we call the photoresist. From there on, the resist is transparent. This is still with a light beam that goes through a lens. So this is an old technology in that sense. That would have to be at best deep ultraviolet, 193 nanometers. In the EUV range, there are no lenses. And you imprint a pattern onto the resist material. Then it becomes either soluble or insoluble, and depending on that, you call it a positive or a negative tone resist. And afterwards, you develop it. This is typically some wet washing procedure, which means that the structures that you imprinted are left behind, and then you can functionalize them. So you first etch structures in, and you can implant ions to get a certain desired electric functionality. After that, you get rid of the resist, and you start all over again. And you can build layer by layer up to hundreds of layers in modern ICs. So this is really this whole process that takes this whole fab where one costs 10 billion with 1,000 steps involved. We've condensed here into a little circle. So I'm mainly going to talk about today what's happening here in this illumination step. Also why I put it in the center. And that's sort of where these lithography machines come into play that are made in the Netherlands and also very much in the US, I should say. There's a large part of ASML that's actually in the US. Particularly the light source is actually developed in the US. It's Cymer is the former name of the company in San Diego. Now, how do these machines look like? It's like this. It's a huge machine, it's probably the size of half of the room or so. We heard the cost yesterday. It was about 300 million for one. So it is probably the most advanced tool. If you ask marketing people at ASML, they will say this is the most advanced tool that has been built by humankind. I'm not sure how that compares to the rockets that were sent to the moon, but okay, that's what people tell you. So how does it work? Very roughly, there's a pretty insane way of making this EUV radiation, and that is from molten tin. So there's a high frequency tin droplet generator, and that's hit at 50 kilohertz with an extremely high power CO2 laser. And that basically vaporizes the tin, makes an ultra hot plasma. It's in terms of a temperature hotter than the sun. And that creates fluorescence. And that fluorescence is what you use to write chips. But because it's so hot, the fluorescence lies in the extreme ultraviolet part of the spectrum. So it's basically black body radiation, right? You know, if the temperature goes up, then the black body radiation shifts. We have a black body radiation of about 14 micron, I believe. So you need to get pretty high to go to 13.5 nanometers. So this is basically how that works. You have these droplets here that are fired by tin, the tin droplets that are fired on by a CO2 laser. The light is caught and then directed with a few mirrors onto a target, and then onto the wafer where the wafer is being printed. So basically, source is a very big part of the research. That's also what part of my colleagues at ASML work on. The other part is all the materials that go inside a machine. It's by no means possible to reflect even a bit of light at 13.5 nanometer. Nothing wants to reflect that light. So very specific optics have to be designed for that. And then lastly, and this is what I work on, you need to make sure that you're actually printing what you want to print. Otherwise, you will never reach the 90% yields that are required in modern fabs. And that's sort of what metrology has to take care of. So how do these chips in the end look like? Well, obviously, they go into many important things, including your phones. So we zoom in here. You take the CPU out of the phone, a chip from Apple. They are made on such a wafer from one of the dies here on the wafer. And if we zoom in here, what do they look like? This is here really a whole three-dimensional architecture of many different structures. At some point, we get the 3D view. Here we go, of the different transistors that are all interconnected with copper wires. And the typical dimensions, by now, maybe even a bit smaller than that, are critical dimensions of what is indicated here, 50 nanometers. So the critical dimension is the smallest size, the smallest width of any of the features. And then the overlay, that's even smaller. That's how accurately they are positioned on top of each other. So that's about 4 nanometers. How many silicon atoms are that? 4 nanometers. What do you think about that? Yeah, so this is only how much the overlay is in typical chips. So the accuracy you need to reach and in the processing is then typically 1/3 of that. So we're talking about 10 silicon atoms with the precision that this needs to be printed across a wafer. That is 30 centimeter, which is 12 inch. Yes. So this is the insane accuracy that is needed here. And that you need to keep in mind. We now need to have metrology tools that verify at every single step that this is working. Yes. So here again, highlighting the overlay and the critical dimension. So this would be one of these structures that we saw on the last slide. We zoom into one of these guys where you have this is basically a single transistor, source, gate, and drain that is shown here. Basically, this is the same as this is a PowerPoint visualization of the gate here. Then I already indicated this would be the critical dimension. This is the width of that feature, and the overlay, how accurately these are printed on top of each other. And the typical dimensions we're talking about is that the error we can allow ourselves is about 30% of the critical dimensions, and 10% of the the overlay error that we allow to have is 30% of the critical dimension, and the critical dimension error is only 10% of that. That means the critical dimensions have to be printed with 1.5 nanometer accuracy and the overlay with 4 nanometer. So at 1.5 nanometer, this is, I think, then already less than 10 silicon atoms. And again, what we already said, all that on 12 inches. Insane requirements. How would you do that? You material scientists, you know all type of characterization techniques in the world. How would you characterize that? I'm sure you know some techniques that have that resolution. What do you think? That would work, yeah. Yeah. Yes. Any other ideas? Yeah, all that. It's interesting. So it's all correct, and they all have their place, these techniques, but they all have one issue, and this is sort of the second point I put in here. In general, what you're saying is, of course, true. All these techniques would work. But what is very important is that you are able to do at least some measurement on every wafer that you're making. And you have hundreds of wafers per hour that one machine is printing. So some of these techniques even need to go inside the machine of ASML. So you can't really put an STM or so in there. Also can't put a transmission electron microscope in there. And last but not least, simply also because it's too expensive. So you need to think of ways that are really fast and also non-invasive to do that. So things like X-rays and laser interferometry, that in principle is great because it only means you shine a light beam on something. So that's why it's always very useful to have optical metrology techniques that can at least do some of the quick inspections. If you then see something's really gone wrong, then all the fabs still have TEMs or other forms of electron microscopy to do the real careful checking. But a lot of the bulk work is typically done with, I would say, almost relatively simple optical techniques. Now, what actually has to be measured? So same picture again. Now we've taken an actual image of what such a single transistor unit looks like. Here we go. So here it still looks pretty straight, but if you then look at what these lines actually look like, is that there's a lot of variation. You see there's a roughness of the line, which is called line edge roughness. There's sort of a variability of how thick this line is, sometimes getting a bit thinner towards where it was etched. It's a line width variability. Then there are sidewall angles that happen in the etching, and many other things. So these are all various parameters that in the end influence device performance. And all of these may have an effect. And depending on the application, they may need to be characterized. So what you also see is some of these structures look kind of periodic, but not all are. That really depends on the device that is being made. I will talk about that later. However, if you can measure on a periodic structure, is hugely advantageous. There are two main reasons. I'll start with the second one listed. It gives you a lot of signal. If you have one scatterer, it gives you one scattering event. If you have two, it gives you more. And because it's the electric field that scatters and you detect intensity, your signal actually goes up with n squared, where n is the number of scatterers. So it gives you a lot of signal. There's almost nothing that scatters light as efficient as a grating. That's why we use it in spectrometers. And the second one is that optical phase provides sub-wavelength accuracy. Does that make sense to you? Because when I heard that the first time, I thought, oh, that sounds weird to me, because I once learned there's the upper resolution limit. And then you think, what do you really want with these optical techniques? We're only going to reach a few 100 nanometer resolution. Any idea why optical phase gives you that accuracy? Yeah, the idea here would be, typically you say, if you come, say, with 800 nanometer light, you wouldn't get substantial diffraction from a 200 nanometer structure, or you would get nearly no diffraction. Still, the phase will tell you something. We'll come to that a bit later on. Also, the wording, it's in the detail here. I'm saying sub-wavelength accuracy. It's not resolution, really. It's accuracy that you get. Here we go. I'll just have to stand here. Still, of course, most devices are aperiodic. So basically, we're left with two options. We either don't measure on the device, and we say we just sacrifice one of the costly real estate on the wafer for a metrology marker, and we put a periodic structure in there. And we know that the periodic structure is sufficiently representative of the device. That's actually what's done in most cases. Simply because it's better to sacrifice a bit of real estate for chips than to have a technique that's slow. And the other option is, okay, we really need to measure the whole device, and then we need a full field 2D or 3D imaging technique. And then that can be optical or E-beam, can be transmission electron microscope, but typically this is not what was done for the bulk of the measurements. Here we go. Okay, so the outline of the talk is we're basically in this point 2 now, right? This was my introduction. Now we actually look what people do in industry. We can divide that into two groups mainly. This is what's happening before exposure and after exposure of the photoresist on the wafer. The before exposure techniques are in fact happening inside the lithography machine. That's why these lithography machines stay here. That's why these lithography machines are often called twin scan, because they're handling two wafers at the same time. One is actually for lithography, for the exposure, and the other one is being measured, and then it's shifted towards exposure. So here you have the wafer that's being exposed, and here you have the wafer that's being accurately mapped out. See how that looks like. So you see a wafer comes in here. At the same time here, a structure is printed. And then you have several sensors here. We talk about them in a second, that map out both the height variation of the wafer and the XY variation. That's done at several locations because the wafer is warped. It's not defined by one X, Y, and Z measurement or two. And then once this is done, yes, the wafer is getting shifted over. That must happen very accurately because no new measurement is done. And then the exposure happens. So it's done fully simultaneously, that there's no time that's being lost for this alignment and leveling processes. Now, why is that actually needed in the first place? It's mainly because there are actually a lot of height variations. If you put a 30 centimeter wafer on a table, it's not flat. It's buckling and warping like crazy. So that's why it needs to be mapped out. And then there are film thickness variation also because that is not nearly at the uniformity level of the few nanometers that is needed. So it needs to be measured. Then this information is being fed through the lithography column, and the depth of focus can be accordingly varied. Okay. So the two sensors that you saw there on the left were what's called level sensor. That's this one that shoots a laser beam here and detects here, that determines the height position, and the alignment sensor, which measures the XY location of the wafer. So this one is very important to get a good critical dimension uniformity and alignment sensor. It's for the alignment position, that's very important that subsequent layers are getting printed accurately on top of each other, which is what's called overlay. So generally, how does that level sensor work? It's basically a principle of optical triangulation. I think it's conceptually really the most simple sensor you can come up with. You project a grating-like structure onto the wafer and imagine the wafer has a certain height variation. That means the beam is getting shifted up and down. You put a detection grating with a similar pitch in the beam, and that simply gives you an imbalance of the intensity of the plus and minus first diffraction orders that is being generated. And that imbalance gives you a height. So what you're actually doing here, you're translating a nanometer height variation into an intensity measurement. You can measure intensity over orders of magnitude with a high accuracy. And that's where this nanometer sensitivity comes in. It's not a resolution in that sense. You're still projecting micron pitch gratings on the surface, but you can measure very accurately if there's a very slight position shift that translates into an intensity shift. Now, this is, of course, looks very simple, but it's never that simple in real life. So suppose you have an actual material, so you have a silicon substrate, you have a product layer, and there can be a hard mask that's a specific etch mask that's used instead of photoresist if a soft material is supposed to be etched. Can be in a bark that's an anti-reflection coating and resist on top. So many, many different layers. So indeed, if you have a height variation or a shift and you only have a top reflection, then it's easy. But in reality, it looks like this. You get a reflection at every interface, right? And that needs to be taken into account. So there needs to be very accurate modeling and knowledge of the stack that needs to be fit in the model. And then something can be figured out there. So it's still a computationally heavy technique. Otherwise, you get what's called a height process dependency error. So that means that depending on the process, depending on the layer you have in there, you might measure a height that's not correct. Okay. Now to the alignment sensor. So that's the one that shines here from the top. That's what measures the XY positioning. The idea of the alignment sensor is that the lateral position information, so the X positioning or Y, is encoded in the face of the scattered wave. So you can think of a small point-like marker on a substrate that's illuminated by a plane wave, and that will create a scattered spherical wave. So you imagine you have that, and now you shift that marker around. What do you think? How does a spatial shift of a marker imprint itself on a laser beam? It is, absolutely. So we are thinking of what's happening in focus of a beam. So that will be the near field. And then we want to see we're going far away. That's the far field, right? These two operations are related by Fraunhofer diffraction. And that's simply a Fourier transform. So you shift something in the near field, and you want to know what happens in the far field, which is the Fourier transform of a function that's shifted in space. What happens there? In the far field. There will be some divergence, yeah, but something else happens. Yes, the phase shift, exactly. So mathematically, there's just a Fourier shift theorem, right? The kernel of the integral, if that gets a position shift, then that means that in the far field, the solution of that integral actually only gives you a phase shift. Yes, that is exactly the reason. Thank you. I would have said it in with that, but you said it better than me. So you basically get any position shift here as a phase shift. And already in the previous example, I showed we can measure phases from interferometric techniques or from some tricks with gratings with a very high accuracy, because we can just translate that to intensity measurement. So that's where the sensitivity comes in. It's not a resolution. You're not going to see a 5 nanometer pitch grading with it, but you can determine if a 10 micron pitch grading is aligned with an accuracy of 5 nanometer. That is the trick here. So that is the phase shift you're getting from given wavelengths, and then incidence angle theta I, and angle of the outgoing scattered wave theta S. Then if you replace the scatterer with a grating, then we know that in the we get an enhancement of the scattering in the well-known directions that we get from the grating equation. So that corresponds to the different orders, diffraction orders of the grating. So we can plug in basically the grating equation for the relation with the angles. And then what we get is that the phase shift directly relates to a position shift of the grating divided by the pitch. And of course, the pitch you know, because that's what's being printed into alignment marker. What you also see from there is you need diffraction, right? Because it depends on the diffraction order. So the zeroth order does not contain any information. You need to have a diffraction grating. Even if you work with visible light, that means you need to work with a micron pitch grading, but you can use that to determine the position really with nanometer accuracy. So how does it look like here? That's an illustration of the incoming wave on a alignment grating, and we get a plus and a minus first diffraction order. And the lines represent the maxima of the electric field. And that's our alignment grating. So if we shift that in X, then what will happen? You get a phase shift of these beams in the first and minus first diffraction order. So there you can directly see you get an encoding of the position into the phase. So we need to measure that. How does that work in a sensor? You basically take a light source, you diffract it from the grating. The zeroth order is getting blocked out. So it's called a dark field measurement technique. And then it's getting refocused on the detector. Then the crossing of these two forms an image of the grating. So that's what the image on a camera would look like. Basically, you just see a fringe pattern with 100% modulation depth. The challenge here is you don't really want to use a camera that's slow, and it has a comparatively high noise level compared to a photodiode, which also is cheap. So we like to use the photodiode. So basically what you do is you do the same experiment, but replace the camera with a photodiode. And then the trick is you put an additional reference grating in front of the diode. So that's the same grating that we would put, in principle use for the alignment target. And that means when you now shift the alignment grating, you either align the lines of this grating on the reference grating, or you shift them such that the light goes through. So you get a signal that looks like this, just a nice periodic modulation on the photodiode. Now from that, you know when you go through the grating, but you haven't really found the location because you get a lot of maxima on the same height. So that doesn't really get us there yet. There the trick is to use two gratings. So you basically put two gratings in the alignment wave and two gratings here that have slightly different periods by about 10%. And what you then get in the transmission function is that they are slightly out of phase, and only at the location where you actually want to measure their in-phase, as you will detect the total intensity from both gratings, so the sum of the two. You get a peak here, and that is where your actual position is. So how does that look like? So that's the same setup as before. We have a stage here that moves diamond grating, the laser that goes on it, and we now look at what the interference pattern looks like, what the detected signal actually looks like. So that's still the spatially resolved detected intensity that you would get with a camera, and then here what you would detect with a photodiode. And here is the transmission function of the reference grating that stays the same because it's just in place there. So while you scan the wafer stage, the interference pattern that you generate will also move. And depending on how it is aligned with the grating transmission line. And what you detect is the integrated signal thereof, which then clearly peaks once you have found the exact location. And that really works then with a few nanometer accuracy to locate a wafer.
So maybe not everybody knows this, but of course, if you're going to measure position with nanometer-ish accuracy here, you're moving the wafer with nanometer-ish accuracy.
Yes.
Does anyone know how that's done? Usually. Actually, don't know.
Yeah, very advanced stages, but they have piezoelectric controls. Yeah. 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 And with an optical feedback, right? So that is what's providing the optical feedback in there. So it's a relatively simple technique in terms of that it's just basically linear interferometry that's being used here. All you have to keep in mind, this basically needs to measure a marker in 20 milliseconds with this accuracy. That's the time that you have for one marker. Several markers need to be measured. Also, the leveling needs to be done. And that cannot take longer than the lithography exposure process, because otherwise you would literally lose time and money in the whole fabrication chain. Okay, this is basically what I want to talk about, the measurements inside the machine. Any questions on that? Yeah.
So, the method you described, you have a grating at your reference area. How do you, if there's errors in the pitch, so how does that get diagnosed? I guess like, what is, if this maximization doesn't work, is that just kind of like the wafer is gone? Like, is it assuming that the pitch is ruined by whatever process that you were doing, or?
If there's an error in the
I guess the pitch that you were expecting.
Yeah.
Versus your reference grating.
I think the reference grating, because it's really something you put inside your detector, that is perfect. That's probably made with a very high accuracy e-beam lithography tool, sorry, and then checked with an e-beam metrology tool, so that you have a sub-nanometer accuracy or so of that, because it's inside your detector, right? So you don't have to change it during the process.
Yeah, but then I guess the pitch that gets put on your wafer, right? In your lithography step.
Yeah.
If that's slightly distorted relative to that reference.
If it's, yeah, of course, the grating itself is produced in the same manner than all the integrated circuits is produced. So yeah, that's a bit the tricky part, right? You're measuring on the marker. So what happens when the marker is worse than the actual device? Yeah, that's why it's not great to measure on a marker. So you wouldn't know, indeed. And at some point, you only would know if you put it under an probably an e-beam inspection tool. Yeah. Any other questions? Yeah. Very good question. Yeah, in principle, you don't want to put a metrology marker into every layer that you're printing. So sometimes they have to be measured through several layers. And that is an issue because there are materials like tungsten or other metals that really do not transmit anything. So how do you deal with that? That's an active research direction that we have. You can think of other wavelengths, or you can think of techniques that bring buried gratings to the surface. We have actually two colleagues of mine that work on photoacoustics. What they do is they launch an acoustic wave in the top surface of the material that travels through the material and then brings an image of the grating back to the top surface by straining that a little. And then you can measure that at the top surface. So stuff like that in the end. Any other questions? All right, then we come to metrology after exposure. So first of all, why do we need that? That's mainly now to control the overlay of layers and the critical dimensions, so really things that happen after etching. Typically, the device patterns that are printed are very close to the resolution limit of what is possible. So any variations in the process directly have impacts on these things. So they need to be checked. It's also simply because we know that critical dimension and overlay are good measures for the electric functionality of the device. In a way, this is totally accepted in the semiconductor industry, but you could also question that in the first place, right? Why do you not put contacts on your material and actually measure the device functionality? Well, because that takes longer, and we know that these are pretty decent measures, and if that's not there, then probably the device is not going to work. So if you want to minimize loss, the CD variations must be very tightly controlled. And that also requires very densely sampled CD measurements on maybe not every wafer, but at least whenever a little bit to the process is changed. So typically that happens sort of if you look at this chain in a semiconductor fab. You first have a lithography cluster that does the exposure. Then there can be metrology directly after developing, so that's only after the photoresist has been developed. And then there's typically also after etch metrology. This is mainly what we will be, well, we will talk about both of these things. So it's basically after development and sometimes after etching, what we are looking at now. Yeah, we talked about this already a bit. In principle, E-beam techniques are great for that purpose. Also, AFM, they have sufficient resolution, but they're either too slow or invasive. That doesn't mean they are not used. They're absolutely used. They're in every fab, but it's not what you can have fully integrated in almost every step in the process. So that's basically good about optical microscopy. It's very fast, it's non-destructive, but it doesn't have the resolution. It can have accuracy, but not the resolution. So what is usually used are model-based techniques, what's called scatterometry. That can deliver sub-nanometer precision and in principle also 3D profile information. So how does that work? It's, to me, also rather surprising that something like this can work. It's, again, a very simple setup. You use a broadband light source to illuminate a wafer. The light is being collected and then spectrally resolved. This is now really done on device pitch, on pitches that are representative of the device. So 20 nanometer, 30 nanometer, something like that. Typically also still on metrology markers, so on structures that you know very, very well. Now this is done with visible light. So what's going to happen? You shine 800 nanometer on 30 nanometer type pitches. I see confusion. The answer is not much, really. There is a bit of an evanescent wave coupling into the material, and that depends on the pitch. You can think, for example, if you have an incoming light and you have a grating like this or like this, there will be a different coupling into the different, basically, waveguiding modes that are made up of the grating. That has a little bit of an influence, has a bit of a wavelength dependence. So if you measure polarization and wavelengths and all these parameters, you can get an idea of the underlying structure, but there's no concrete inverse relation as we have it for diffraction, right? Diffraction, we know there's just a Fourier transform that goes from the near field to the far field. And that doesn't work here for this evanescent field coupling. So the way that works is it's basically linear spectroscopy of these structures. You just take the zeroth order because there are no higher orders that come from these, spectrally resolve them. You get a spectrum, and there's a library of 100,000 pre-simulated structures. You always do it on the same metrology target, so you know what you expect. And then it's basically a library search to match those. So it's a very computational approach that's taken here, and certainly something where with AI these things can in the future probably be sped up. As I mentioned, this is typically happening in scribe lanes. So if you look at the dice, and there are these dedicated lanes, and these have metrology targets, and they are fairly simple for that approach. That's why you still have a chance with these model-based approaches. And finally, depending on if you measure on a CPU or on a memory-like chip, there is a chance that you can actually work directly on the structures. And that is mainly because memories are typically almost perfectly periodic structures. Whereas CPUs, they're nothing like periodic structures. So memory is one of the things where people can actually directly measure on structures without the metrology target. Now then, finally, for overlay, how to control the alignment of two layers on top of each other. What's typically done, there are two approaches: an image-based overlay. You just put two gratings or multiple gratings into a marker, and you put one in the top layer, one at the bottom layer. You take an image of that, and then you simply try to get an image with a lot of photons so that you can determine the maxima of these lines with a high accuracy. And from that, you can determine an overlay shift. So it's image-based. You can, again, not resolve very fine structures, but you can determine the maximum of a point spread function very accurately. And then finally, diffraction-based overlay. I think this is a very neat technique, again. You work, again, with a relatively low pitch grating with micrometers. You shine a beam on it. And what you have is, if you have two gratings, they're perfectly aligned on top of each other, you get equal minus and plus first diffraction orders. If they're not perfectly aligned on top of each other, well, you can say this almost looks like a blaze grating, right? So you will get an enhancement in the direction of the blaze. And again, this gives, if you only measure the intensities of the first and minus first order, you can be extremely sensitive to any small variations that we have there. This is this technique of diffraction-based overlay. Exactly, and you need to have both directions, and you do that with bias gratings to have any tool-induced shifts. Thanks, forgot that. All right. Any questions here? It's going a bit long, so I'll keep going. So we've basically now gone through the main techniques that are used in semiconductor metrology. Level sensor, alignment sensor, and scatterometry, both for CD and overlay. They're pretty straightforward concepts that all come from interfering plane waves. It's all with standard wavelengths from the near UV visible mainly to near infrared. But it's a significant challenge to measure robustly with that, right? So sometimes you have layers that bury your actual metrology targets. These computational approaches and scatterometry are often not very unique in the solutions that are found. So there are a lot of challenges. So some of the challenges that are considered particularly important are listed here. There's basically, with these techniques, almost no decent at-resolution inspection, with the exception of critical dimension scatterometry, but that's very model-based, so it's also not very direct. And of course, it would be nice to actually measure on something that is really fully representative of the device. At some point, an 8-micron grading is not very representative of a 10-nanometer device structure. We usually measure with periodic structures, but that is often not the case in an actual device. Only memory is really periodic. And all these wavelengths have very limited penetration depth, so you cannot really, they're not very well suited for 3D processes. So my challenge to you, how can we address that? There is one, I find, semi-obvious solution to do that optically. Two? Yeah. Okay, maybe it's not so obvious. No, so what is very much pushed is now simply shorter wavelengths. Shorter wavelengths help with a lot of these things. If you make the wavelength short enough, you diffract from a 20-nanometer structure. So we're talking about soft X-rays. If you work with this, you have diffraction, you can in principle do a full field imaging experiment at this wavelength. It will take very long, but it's possible. And if you go in the soft X-ray range, the penetration depth becomes more favorable. If you go in the hard X-ray range, you can measure in transmission through several micrometers. In the soft X-ray range, you can deal with a few hundred nanometers, which is already pretty good. So soft X-ray seems to be one of the ways to go, and that's one of the main parts in my research. So in soft X-ray, the idea is still to work with scribe lines and dedicated metrology targets, but now at resolutions, 20 nanometer pitches. The pitches we're dealing with still illustrated here. It's currently somewhere between 14 and 45 nanometer, but that's going down to below 10 nanometer in the next years. And yeah, the main motivation is indeed that large pitch targets are at some point simply not representative anymore. You might measure a good overlay with your 10 micron pitch grading, but that's not the overlay that's actually existing in the device. The other part about soft X-ray that is pretty nice is that it can measure through a lot of buried layers. So that comes to one question that was there earlier. Particularly these hardened masks, these special etch materials are often completely opaque for visible light. And that's a bit better in the soft X-ray range. So showing here the absorption coefficient of a lot of different materials that are shown there on the left in the soft X-ray range, and in the visible wavelengths range, it's the same Y scale. So higher value of K, higher absorption coefficients means more light is absorbed. And you see, especially if you go in the 15, 10, 5 nanometer range, it's considerably lower, about 2 orders of magnitude than what you get in the visible. So that's good news. You can really go through a few hundred nanometers. So the idea for soft X-ray metrology is basically like a diffraction-based overlay. You deal with several gratings that are lined on top of each other, but now you do that with nanometer pitches. So you need to generate soft X-ray lights, reflect that onto your metrology target, detect all the diffraction orders, and then you get your overlay and critical dimension measurements. Sounds easy, right? And it's a bit of a marketing sentence I once heard from ASML, but I liked it. What extreme ultraviolet lithography could be to deep ultraviolet lithography, soft X-ray could do to optical metrology. So all the advantages I think I've mentioned, it actually has a wavelength range that matches device properties. It's in principle, there are broadband sources available. We'll get to that. It's a strong decorrelation between parameters of interest. And it's suitable for high throughput because it's an optical technique. However, how do you actually make these soft X-rays? One idea is, it was literally idea to put a little synchrotron in the semiconductor fab, but it quickly gets a bit too expensive, especially because metrology shouldn't be too expensive. But there was a, by now not so recent development anymore, to process that, well, for industry, it's still pretty recent, was discovered in 1988. That's high harmonic generation, so 36 years ago. But then it took very long until something came out of it. It's in principle pretty simple. You shoot a 30 femtosecond laser pulse into a gas expansion. Highly nonlinear light-matter interaction happens. If you just send it on a grating, you see a very broad spectrum coming out. It looks like this. So in this direction, we have wavelengths, and this is a free divergence of the beam. You see very discrete peaks of light, and these are odd multiples of the fundamental frequency. So this is done with 1300 nanometer. So what we're seeing here are multiples of the energy. It's about 1 electron volt of the 1300 nanometer. And that goes here from 60 nanometer to 10 nanometer, ultra broadband. It's a huge wavelength range that can be spanned like that. Oh, that's now we go very deep into the physics. There's in the process of high harmonic generation, there's I'll show that on the next slide also. There's a photoelectron generated that's laser driven, accelerated, and recombines. And that recombination step is the time inverse of photoionization. So you get characteristics of photoionization. That's the so-called it's an atomic structure effect of the generating atom, basically, that is underlying that. That was by no means trivial. There was a few very important papers in PRL about 10, 15 years ago that elucidated the origin of that minimum. So how does it look like in the simplest possible version? You have a vacuum setup, first with a gas expansion to generate the light. and then a setup to analyze the radiation. If you want to do something with it, then it's a much longer setup with mirrors and detectors afterwards. Now we zoom into what's actually happening in the first vessel. So this is our gas expansion. The gas comes out to both sides. The little green dots are our noble gas atoms, say argon or neon. Helium is also used, and that's our ultrafast laser pulse. Oscillating electric field under a Gaussian envelope, the full width half maximum of which is the pulse duration. Now this is a very strong pulse. In the peak, it is on the order of the Coulomb potential of the outermost electron. So it starts really pulling and pushing on the outermost valence electrons. Once the field is strong enough, the Coulomb potential gets bent so much that the outermost electron can tunnel out the laser field. Once the field changes sign, the electron can come back. It's accelerated more, and upon recollision, all the energy picked up in the laser field is released, and that's in the form of light. And that's the soft X-ray pulse that comes out. So not only is there a soft X-ray pulse that comes out, it happens in a fraction of an optical cycle. So it's also the shortest pulses that can currently be generated. You can find it silly or not, but it's in the Guinness Book of World Records for the shortest pulses, light pulses that can be generated. So it's of attoseconds duration. Yeah, you can see it like this. So it needs to be by default ultra broadband, what comes out. So that's also what you can kind of get already from the spectrum. It should be, if it's coherent, it should be an extremely short laser pulse because it's so broadband. Little challenge question for you. This one is a hard one, probably. Of course, we want to actually generate very short wavelengths because that's what will help us to see the smallest structures. So from this cartoon that I showed you, how would you go about to make the wavelengths you generate with high harmonic generation to make that as short as possible?
We're taking down electrons.
Yes. No. Yeah, that's one of them. So that's you can go to helium, but that's it, basically. So there are other things you can do that will get you a bit further. It's tricky. So the idea is basically, also in view of time, I'll resolve that. I think you want to pull out the electron as far as possible. Give it as much kinetic energy as possible. So you can go higher in intensity, but at some point you just ionize everything. That gives you a huge amount of plasma, and that prevents any coherent buildup of radiation. So that doesn't really work. What you can do is you can increase the cycle duration. What that actually means is you go to a longer wavelength. If you do that, there is more time in an electric cycle that the electron can pick up kinetic energy, and then upon recollision, you get higher energies out. So it's a bit of the counterintuitive thing. You have to go to longer wavelengths with your fundamental driver to get shorter wavelengths out. The problem is if you do that, the flux goes down. So, yeah, so there is no free lunch here, unfortunately. Yeah, what is with that? This is related. Yeah. Yes, it's both the ponderomotive force that is at work here, right? So it's basically the ponderomotive force of the electron, and it's also, I think, the ponderomotive force that keeps the particles in check in tweezer. Yeah, a lot of these concepts of that come together here. All right, I think I can skip that part. Spectra, and in case you have noticed, this is actually what was awarded the Nobel Prize last year for these three scientists. Now, what we can do with that, we can make basically diffraction experiments on complicated structures. This is from an SPIE contribution from a bunch of scientists at ASML, actually. Forgot to put the reference, I'm afraid. But you get relatively complex diffraction patterns that almost like an X-ray diffraction you can now use to reconstruct these nanometer structures. One thing that we are particularly working on is to add ultrafast temporal resolution to that aspect. So we sort of build a simple version of that setup where we mainly look in the beginning at the zeroth order. But then in the next step, we want to use that for actually following the electron dynamics that happen between different layers. So the structures we started with is that what we already see in the zeroth order is a simulation. We get a very strong variation of the signal as function of photon energy for different group heights. This is basically because we get different interference conditions from the reflected waves at the top and the bottom of the surface. And for the measurements, we see both here and here, we get a shape that more or less looks like what we expect for the structure, but there's still quite a bit of discrepancy. We have a good idea why, but that's sort of what we're working on. The ambition here is that we get the structural information and can combine that with temporal information and the unique element specificity that comes with X-ray absorption. It's a very nice paper here from a former colleague of mine who simply made a junction out of 3 materials, nickel, titanium oxide, and silicon, photo-excited that, and then he could follow what is actually happening in the individual layers as a function of time, because we know in the X-ray range that different atoms always absorb at the same energies, because these are inner valence absorptions that we're doing, so they're not much affected by chemical bonding. It's the reason why we use synchrotrons for all kind of X-ray absorption spectroscopy. So by doing that and combining that with structural measurements, we will push for an all-optical inspection method that it actually allows us to follow electric currents and therefore device functionality. How am I doing on time? 5 to 10 minutes. I'll skip this part and then I'll come to the last one. Yeah, so we also did several experiments now. Let's maybe start here, where we generate harmonics directly from solids. Interestingly, it was 1988 that someone discovered this high harmonic generation from gases, and then it took until 2011 and someone tried to put a solid in the laser beam, and it also worked. But the energies that come out are not that high. So in that case, the first demonstration, people managed to generate harmonics up to about 100 nanometer. This is one example from our lab where we go to about 30 electron volts, 25, that's 50 to 40 nanometer. So it's still pretty high energies, but not nearly as high as we can go with gas harmonics. Still done at intensities that are below the damage threshold, but at conversion efficiencies that are much lower than in gas HHG. The pictures how that works are relatively similar. You can also say you create an electron in a hole, which you now accelerate in the bands and recombine. Now, what we thought is interesting, instead of using that as a light source, we can directly do metrology with that, because that actually eliminates the need for a dedicated light source, and that makes up for a bit of the loss that we have in conversion efficiency. We started with simple structures, again, some gratings, micron pitch that we imprinted on a surface, generated harmonics. If we go from the flat side, we just get discrete harmonic emission in the 100 nanometer range here. If you then go on the grating, you see very distinct diffraction order. So you get diffractive harmonic emission. Interestingly, you see the emission from the 0th order is getting completely killed. This can be modeled because we basically introduce a phase grating where there's a phase delay induced between these two. If you get that to exactly pi, then you get no 0th order. With the height information, we can also model that and get a pretty good agreement. Of course, you can revert that if you don't know the height. You can use that to determine the height of such a structure. And that is where sort of the idea for metrology comes in. And we also did that in this paper. That gives us a pretty decent accuracy here of 80 nanometer was the height of the structure. You can go to more complex structures. So you go to a 2D periodic array, generate harmonics from that. Looks like this, almost like an XRD pattern. Then you can run a phase retrieval algorithm on that to go back to the actual image in the near field, which is here. And of course, we can also go to aperiodic structures, where we basically, what we measure in the far field is a Fourier transform of this one. If you don't know what the Fourier transform of a smiley is, I put it here for you. Okay, what we learned from that is, in principle, soft X-ray metrology can probe nanostructures and ultrafast dynamics, possibly also providing a novel measure of device functionality. But metrology concepts and source itself require further developments. What I haven't shown you, but you'll believe me, is we did experiments how to optimize high harmonic generation a bit to make the efficiency higher. which is still pretty low. We're talking about 10 to the minus 6 conversion efficiencies. But what we also learned in that process is we are really good at making it worse. So whenever you try to optimize something, usually you make it worse. And then it took us a while, but at some point we realized this is actually maybe even more useful to be able to make it worse. There's one example where we generate harmonics from niobium oxide, a correlated material. You add a pre-pulse and you get these spectra. It's really visible, low harmonics, third and fifth. You add a pre-pulse and you see you completely kill the emission if you do that. And what we can do with that now is take an inspiration from mainly this guy here, Stefan Hell, who used the possibility to control fluorescence for super resolution microscopy. So instead, if we now generate harmonics with a very strongly focused beam, we can typically generate over a micron, maybe 500 nanometer resolution volume. But if we now give a pre-pulse that deactivates, give that a donut shape, then we can narrow down this emission far to below the diffraction limit. So it's inspired by stimulated emission depletion. That's something we are working on. So very much in the process of getting this to work properly, but a pretty convincing proof of principle experiment is where we focus the generating beam with a long focal wavelengths and then image that with a high resolution microscope so that we can directly see what we do to the emission zone. But what we see is the third harmonic emission from a sample. We overlap that now with a donut beam, and this happens. So we get a drastic reduction of the emission. This is generated with a long focal length. So the diffraction limit is something like 25 micron, which we can still resolve because there are better lenses than that. But we already beat the diffraction limit like that. So we're setting that up now in a proper way with high-NA objectives. And then with that, we expect to go to 100 nanometer and possibly less in resolution in a regular optical microscope that does not require fluorescence anymore. Yeah, so there are actually techniques that are already so multiphoton lithography would be the way. So you need to find a resist, basically, the chemical that does the job. But in principle, yes, I've seen tricks to do that. But for now, I think microscopy is a more feasible application.
So this is the difference in the secondary linear versus with the donut light, right?
Yeah. So the mechanism is probably not like this. It's more that you really craft a new light field, and maybe I can explain that in the last slide because I have one on that. You craft a new light field that doesn't support high harmonic generation in the overlap region. And this was actually a trick that was developed a long time ago to make isolated attosecond pulses, where you make a time-varying field that has one half-cycle linear polarization and the rest circular. When the polarization is circular, you ionize the electron, and then it gets another momentum component and misses the recombination. So we did the same trick here, where we do combine a Y and an X component, pi over 2 out of phase, and we give orbital angular momentum, that's this donut shape, to one of them. The first thing we do is if you just overlap them in time, you get a perfect modulation of the harmonic emission intensity. That shows you basically go from linear to circular polarization. And if we then put in an orbital angular momentum into one of the beams, then you indeed see that you get a regular point spread function here, and you get a reduced one in the minima. This was a 1D step and not a 2D donut. So it's basically by creating light fields. What you're saying to make it a material property is possible too, but I find it a bit less favorable because then it's not general, right? But if we can come up with ways to synthesize light fields and make the deactivation a property of the light field, then it should work in almost everything. Okay. Yeah, sorry, I went a bit over time already. So yeah, these are the people that do all the work. Also, thanks to the funding. And if you have any questions or want to talk more, that's my email address, but I'm also still here.
people want lunch. Thank you very much for the wonderful talk. That was very good.